Hi, everyone. Thanks for joining us today. So before we start, a few words about myself. So maybe I can just go with my Twitter profile because it summarizes everything concisely. So I work as a lead data scientist at OLX. OLX is quite a big company, which is an online marketplace in many different countries. For those who are joining from India or Pakistan or some European countries, you already know OLX. For those who don't, you can go to our website, OLX Group, and check it out. So apart from working as a lead data scientist at OLX, I also have a side project which is called DataTalks.Club. It's an online community of people who love data. This is a really great place if you want to talk to somebody who is interested in different data topics, including analytics, data engineering, machine learning, all data-related things. So you can go to DataTalks.Club and you can join our Slack. Then, last but not least, I am also an author of a book called Machine Learning Bookcamp. And actually today, we will go through one of the chapters. So for following along today's tutorial, you do not need to have a book. But just for you to know that if you want to know more about this and there are other things you can learn from this, it's based on a book. And there is a website for the book called mlbookcamp.com. And all the code that I'll be writing today is already available in the books website. So if you go to the books website, then go to, there is a link to GitHub repository. And then all the code for today is available in this repository. So you don't need to have a book for that to actually go and check GitHub and take a look at all the code. And for today, the plan is, so we will be doing an end-to-end tutorial on training a model in Keras and then deploying this model in AWS Lambda. So the problem we have for today is clothes classification. So imagine you have a picture of clothes. So you have clothes here. So this is like a hoodie. So you can take a picture of this hoodie and you want to classify to build a model to understand what is on the picture. So you will take a picture of this and the model would tell you, okay, this is a hoodie, or this is a t-shirt, or this is pants, or this is dress, or this is something like this. So imagine if you're working in an online marketplace like OLX, but maybe that focuses just on clothes, on fashion items. Then maybe you want to have some sort of a model like that to help sellers decide which category to put their items in. So the problem is simple. So this is the plan for today. So we'll start. So there is a data set for that. We'll start with exploring this data set to see what is there, how we can use the data from there. Then we will start with training a simple model on top of this data set. Then we'll make the model a bit more complex. We'll try to tune some parameters. Then we will make the model even more complex, add some dropout and enlarge our data set with image augmentation techniques. If you don't know what it is, don't worry. We will talk about this in more details. Then we'll see how we can actually use this model for making predictions. First in a Jupyter notebook, and then we will deploy this model using TensorFlow-lite and AWS Lambda, and this model will be available for actually querying. So that's the plan for today. And I wanted to mention that all the things I talked about today, they are available. So there should be links here in the description to the YouTube channel. So you can check DataTalks.Club, you can check the book website, and you can connect me on different social networks. And again, to check the repo, the code repo for the book, you go to the book's website, and then there is a link that brings you to GitHub. So let's start. So the first point we have for today, and by the way, I do not have any slides, so it will be a live coding session today. So the first point for today is exploring the clothing dataset. So this dataset is available also in GitHub repository. So you don't need to follow along this. I'll just show you what this repository is. So it's called a clothing dataset, which is a dataset about clothes. So let me just enlarge it a little bit. And in this dataset, we have different images of clothes that looks like this. So there are many different images, pants, shoes, shirts, t-shirts, things like this. So there are clothes for kids, clothes for adults, and yeah, quite a few images there. So we will use a subset of this data set. So we will not use all the images, but just a subset, only 4,000 images. And we have a link here. This is a small subset where images are already split into train, test, validation data set. And they are also smaller. So we don't need to resize all these images because it takes time. These images are already resized and we can just use them. So let me just quickly show you how these images look like. So if we go to the train part and let's take, I don't know, t-shirts, you can just open any file here and sorry, quite a few files. Yeah, so it's a picture of a t-shirt. So we have quite a few of images like that. And we want to use this data, this training data, to build a model that classifies all the images we have into these 10 categories from dress to t-shirts. So this is how our data set looks like. Yeah, so like, of course, it's this data set is not super balanced. So there are a lot more t-shirts than, for example, jackets. So we don't have outwear. Yes, simply because like a usual person has more t-shirts than jackets. So that's why the data set is slightly, not slightly, there's a skew towards t-shirts, for example. Okay, so yeah, let's start with a simple model. So for this, I use Amazon SageMaker notebooks. So in Amazon SageMaker, you can rent a notebook with a GPU. So of course, like on AWS SageMaker, it's actually, you need to pay for renting a GPU. Instead of that, you can also use Google Colab, which also, as far as I remember, has this option of getting a machine for free with a GPU. I am pretty sure that the example I will show today will also work there. But yeah, I haven't tested it in Colab. I think it will work. It should also work on Kaggle. And by the way, this data set is also available on Kaggle, so you can just go there and take a look. So as I said, it will be live coding today. So let's start. So first, what we want to do is first I want to check if the data is already there. So I already before going live, what I did is I did git clone. So I took this data set that we saw. There's this clothing data set small, and I did git clone in this URL. So the data is already there. And what we want to do now is do the usual imports. So usually this is how you start a project. So you do the usual imports like import numpy as np, import pandas. And also we will need plots. And we will use Keras and TensorFlow for that. So let me just quickly import TensorFlow as well. TensorFlow import Keras. So we will use Keras that comes in with TensorFlow. Yes, and so we can quickly also check the version of TensorFlow when it loads. Yeah, with TensorFlow usually it takes some time to load. Okay, so it's relatively, it's not, I think it's a pretty old version. Okay, yeah, it's fine, it should work for us. Okay, so we have that. And I was actually hoping to use TensorFlow-2, so let me quickly check if I can do this. Yeah, so this is what we need. So we need to, like in SageMaker, so you can use conda TensorFlow-2, P36, meaning Python 3.6, or you can use conda TensorFlow P36, which is an old TensorFlow. So we want to use TensorFlow version 2. So let me just quickly copy what I typed. Okay, and then just to double check that the version is good. Yeah, while it's slow. Oh, okay. Yeah, so this is a good version. So we'll use that because like the second version of TensorFlow, it's better. Like it has more features, and then the built-in Keras is a lot better. So what we'll do next is we want to take a look at the images we have, at some of the pictures, and for that in Keras there is a function called load image. Let me quickly load this from TensorFlow, Keras, pre-processing image, import load image. So this is a special special function that is there in Keras for okay, yeah, sorry, I just got a message for zooming it in a little bit, so I hope it's more clear now. Yeah, so let's load an image. So this function comes from Keras that helps us loading images, and yeah, let's just load one of the images that we have here, which is, let's take a t-shirt, t-shirt. Okay, we'll go train, then t-shirts, and then let's take yeah, this image. So we just use this function, load image, and then we give the file name. And then it just shows an image, which is my t-shirt with OLX logo. And of course, we can have different parameters here because for a neural network, we don't just usually take an image as is, we resize it a little bit. So we can say that target size is, let's say, 299 by 299, and then images resize it. We will use even smaller images, 150 by 150. So this is something we can add to this function, load images. But usually when we train a model, we don't load image one by one. So in Keras and TensorFlow, there is a special thing called image data generator, which we will use for loading images. So let me import it from TensorFlow, Keras, pre-processing image, import image data generator. So this is a special special thing for loading images. So let's say train generator. We first created this generator, and when we say, okay, we want to generate images from this directory, and for that we create a special thing called data source, I think. I don't remember what DS stands for. So we say, okay, we want to load from this directory, from directory, and then what we give inside here as parameters is the directory where we want to read it. In our case, it's the train directory. Then since there is some random element because images are shuffled, we want to set the seed so it's reproducible. And then we say that target size. So this is how large the images should be. We'll use smaller images. And then batch size, this is how many images we use at once for training a model. So we will load 32 images at once. So we have something like this. So sorry, type here. Yeah, and we see, okay, we found 3,000 images and there are 10 classes, different classes. So we can actually see what is inside here, what's inside this data source. So what is inside is two things. So first thing is the matrix X or tensor X, which contains the images. And then there is another array with labels. So we can call it Y. So we can just take a look at what's inside using the next function from Python, because this is an iterator. So we can get the next thing from there using next. And this is how X looks like. So you see that like I think there are 3 channels, red, green, blue. Yeah, the shape of this is, so there are 32 images, and this is the batch size we specified. Then images are of this dimension, 150 by 150. And then finally, there are 3 channels, red, green, and blue in this matrix. And then the Y array looks like that. So this is like we have 32 rows here. And then like we have one here if like this is this column corresponds to some label. So I don't remember which is it. Let's say this is t-shirt and this is dress, right? So one here stands for t-shirt. So every time we have one here, it's a t-shirt. So I don't remember if it's actually t-shirt or not. It's just for an example. So this is how our input data looks like. But actually, like if we go back again and look at images here, like they are it's from 0 to 255 the values. This is not usually what we put in a neural network. So usually what we do is we do some sort of pre-processing before putting it to a neural network for many reasons. So there should be some sort of standardization. So this is what we do usually. So we, let's say, normalize it to a range between -1 and 1, or between 0 and 1, something like this. And for actually training a model, we will use a model called Inception. So there is in Keras, there are a lot of pre-trained model, and pre-trained model means that somebody already trained a model for us, and we can just reuse this model. And we can build our models on top of pre-trained models. So somebody, let's say it can be a company who has a lot of resources, or somebody took care of actually training these models. And these are the models that are available in Keras. So if you just Google Keras applications, you'll find the list. So we will use the first one from here called exception. And this is how we load it. So we say from so from TensorFlow, Keras applications, and then since we use exception, so we just say, okay, we want exception. We import the actual model exception, and then this model has a special preprocessing function that we want to use, and this preprocessing function called preprocess input. So if we take a look at, so this is how our image looks like when we load it. This is unprocessed image. And when we apply our process input function to this image, this is how it looks like. So you see that the value become, like there are some, I think they are standardized, and they go from -1 to 1. So I don't remember exactly the logic there. I think it's something simple. You just, yeah, whatever you have from 0 to 255, it just maps it to -1 to 1. So nothing fancy. So we need to apply this thing here. So for that, we need to modify our image data generator slightly. So we need to say that for this function, the preprocessing function comes from exception. And we do that. And when we again try to get the next batch from the data generator, so we see how the data looks like. Yeah, this data is already preprocessed, so we don't need to worry about preprocessing it, because image data generator takes care of that. So okay, so we have our data, and we have our model exception. So this model is already pre-trained, and what we need to do now is we need to so this process is called transfer learning. So when you take a model that is already pre-trained, and you adjust this model, adapt this model to your own data set. So you take a pre-trained model, like maybe I can show you an example. Like like for those who don't know much about neural nets. So in neural nets, there are multiple layers. So there is some convolution layer that tries to extract features from images. So let's say we have a t-shirt, right? An image of t-shirt. And then there is a set of layers that take a look at the t-shirt and try to create a vector from a t-shirt. A vector is something like a small NumPy array, right? So it turns an image into a vector. And then there is a few more layers after that that look at this vector and try to combine, from this vector, try to predict the final class, right? And when we fine tune, what happens is we take this pre-trained model and we keep only the part that converts the image to a vector. And then we get rid of these layers that are used in the original model, because the original model is trained for some other data set. Usually it's an ImageNet data set. You can Google this, like if you just put ImageNet, you'll find a lot of information about this data set. So usually this is these models are trained for ImageNet, but we don't have an ImageNet data set. We have our own data set. So we get rid of these layers and we create new layers on top of that. So we add our own layers here. So this is the idea of transfer learning. And yeah, what we will do is exactly that. So we will create a model now for that. So let's just call it transfer learning. Oops. So for that, we already imported exceptions. So we already generated the data set. Let me also do the same for the validation data set. So validation data set here, we do it from the validation category. And for those who don't know, so we have a training data set for training, and then we set aside some data that we look at to see that our model is able to predict clause that model hasn't seen during training. So this is called validation. So we have 340 images for validation and 3,000 for training. And now let's train a model. So since we are taking exception model that was trained previously, we call it a base model. So we create this exception model. So we say that weights for this model, they are coming from ImageNet. So it's already a pre-trained model. Then input shape for us, the images are 150 by 150 by 3 channels. And then finally, there is a last parameter, include top. Last parameter that we need. And top is these last layers that are needed to predict classes from ImageNet. We're not interested in ImageNet, so we don't need to include top. And here we will use this model as is, so we don't want to train it. So we say that this model is not trainable. Okay, I hope it works now. Because it now needs to go to GitHub and get some data from there. I did this before the live session, so that should work. So while it's thinking, let me continue typing. So what we do next is we define our model. So this is the base model, but we need, on top of this base model, we need to define our own stuff. And yeah, okay, so it needs to actually get the model. So base model. So sorry, I think I need to. So first we define, okay, like we need to explicitly say that, okay, this is the input of a particular shape. And again, we use the same shape as previously. Then they say that for this input, we feed this input into our base model. And base model. And we say that this is not trainable again. And then the output of this base model is a vector. So we get the vector. So it's actually a bit more complex than that. So let me just quickly draw it. Okay, so let's say this is our image. So this is a t-shirt. It's a good t-shirt, right? So we put this t-shirt into our model. It's exception model, right? And what it gives us is some NumPy array, some tensor, right? So this, I don't remember the dimension. So let's say it can have just an example. I don't remember, like, I don't know, something. Let's say for one image, it can be 10 by 512, right? And what we need to do is now we want to turn this this thing into an array, right? So what we do next is we want to take this thing and just turn it into an array with dimension 512, and I think it's more than 500. I think it's 1 or 2 thousands. It doesn't matter now. Just for an example. So we want to somehow take each row of this thing and take an average and put it here. So we want to do this because we don't want to deal with tensors. We just want to deal with a simple vector, and yeah, usually it makes things easier. So for each row of this thing, we just take an average and put the result into the matrix. Right? So this is the thing. This is what we do. And to do this, we use a thing called global average pooling, 2D, because this thing is two-dimensional, and we want to reduce the dimensionality to just one dimension. And when we take whatever the base model returned, which in this case is this tensor, and we turn it into a vector. And then finally, in addition to this, so there would be a next step. Where's my pencil? So the next step here, we take this vector and we put it through one extra layer of a neural net, and then we have our final prediction. So which will say, okay, this is a t-shirt. Yes, so this is what we need to do. So outputs, in this case, we take the vector and we add the model. So Keras, layers, dense. So we have only 10 classes. So the dimensionality of this vector of this layer should be 10 because we have only 10 classes. And the input to this is vector. And if you see, again, let me so if we take a look at this input, this is so we have this input, and input goes here, right? So then we have the result is this part, the base part. So the base part again goes here, so we include it here. So it goes to this vector, and this vector goes to an output layer. So you have the vector here, and it goes to this dense layer here. So at the end, we have the output. So this is our prediction that we have here. So let me just clean everything. So this is our model. It's very simple. It's just one extra layer on top of the existing model. And yeah, so we just call it model, Keras model. So and we need to specify inputs and outputs. And this is our model. Right, so our model is ready. We need to train it. So for training, we need to set a learning rate. So this is a sort of a speed of training with like how fast the model trains. And we don't want to set it too large because the model will quickly overfit. I will not go into details in how it works, but like this is one of the parameters that you need to set, and this is probably one of the most important parameters in machine learning, in neural network when training the model. So for this, I would refer to this website. It's a course from Stanford called CS 231N about neural nets. And if you're interested in things like learning rate and optimizers, you can check here. I think, like, for example, this neural nets part 3 talks about different optimizers. I will just quickly send a link here. Yeah, so I will not go into details. If you're interested to learn more about this, especially from theoretical point of view, please check this website. So now I will. So what we will need to do is now we need to train a model. So we need to say, okay, we have a model. Now we need to compile it, and when we compile it, we tell TensorFlow, okay, these are the weights. So now everything is fixed. Now we can now it figures out how to do batch propagation, things like this. How to do like this, like basically how to optimize the model. Yeah, so we have compile, and then we say that for training, for optimizing, we use one of the optimizers. Adam. So we will use Adam again. Like there are different kinds of optimizers, and I would refer to the website I just showed, to the course that discuss different kinds of optimizers. Usually, Adam is a good safe choice if you don't know what to start with Adam. And then we need to specify the loss, like what exactly our model will try to optimize. And for that, we use categorical cross entropy. So when we have a multi-class classification problem, so when we want to predict multiple classes, this is the type of loss we usually use, categorical cross entropy. And here we need to specify that we want to, so if I'm going technical, so this output, it returns what is called logits. So this is like a special, like it's not normalized. So this is a number from -infinity to infinity. Usually it's between -5 and 5. And so this is a raw score before any normalization. So we don't have any activation function here. So that's why we say, okay, we want to just take it raw. So from logits true. Again, I will not go into details what it means. I suggest to check at this website from Stanford. And yeah, and then finally we specify the metric we want to track. So in our case, it's accuracy. And yeah, I think that's all we need. So our model is compiled and it's ready to be trained. So now, let's train it. So for training, we use the fit function from the model. We say that we want to train it using this training data set. We want to train it for, let's say, 5 epochs. We want to iterate over the entire data set 5 times. Like actually, you should train it for maybe longer than 5, but here we want to save time. We won't spend too much time here on that. And finally, we specify what we want to use for validation. And then the result of this is a special history object that contains that can tell us how well the model behaves. So let's I don't know what these warnings are, but yeah. So now it should start training. And actually, like let me open Jupyter Notebook. We can also open a terminal and see how well our GPU is utilized. So when we open, okay, in Jupyter, we can also create a new terminal. Okay, it started training here, and in the terminal, we can see how well our GPU is utilized using a special tool called NVIDIA SME. I don't know what SME stands for, but we can see that, okay, our GPU, which is Tesla K80, is utilized at like it's actually doing something. So it's the memory, like there is something in the memory, and then yeah, it's utilized on 81%. If we execute one more time, yeah, so it's an okay utilization of a GPU. So now it will do this, and because we use a GPU, it should be relatively fast. So let's wait a bit. So I saw that there are some questions in live chat. I'll check them a bit later when we maybe finish this first simple model. So let's wait for one more epoch. Okay, so we trained our first model just for 5 epoch, and we can already see that this is the validation accuracy. So like this, our model is 80% correct. So it can, in 80% of cases, on the data that it hasn't seen before, it can predict, it can make an accurate prediction. So what we can do is we can do some visualization. We can see, we can make some plots. So let's do that. I will use matplotlib for that. I'll create a big figure, 6 by 4. And then what I want to plot is, first I want to take epochs from history. And then I want to plot validation accuracy. So it's called val accuracy. And we also want to plot training accuracy and then see how it looks like. So we see that in our case, the training accuracy immediately goes pretty high, right? So it reaches 85% of accuracy, while our validation accuracy is around 75, 80%. So it doesn't really increase. So this is a sign of maybe not overfitting. Maybe there is not much we can do, but we see that, okay, this is increasing too fast. Maybe we need to play with the learning rate a bit. So what we can do now here is we can try different learning rates. So for this data set, the best learning rate is this one. So it's 0.001. And to find the best learning rate, you can experiment with different values. So maybe you can experiment with 0.1, 0.01, 0.01, and so on. And then I can quickly show you, I have a picture somewhere, how it looks like that when we have all three. Yeah, so one learning rate is better. So it's strictly better than the other one. And when we add too many zeros, then it learns simply too slow. So this is like, it just takes too long for us to train a model. So that's why the best learning rate is this one, 0.01. Yeah, and we can train a model with that. So I will not do that right now. So instead, I will probably check the questions that that we have. Oops. So yeah, maybe it's a bit too late to answer this question if there are any prerequisites in attending this workshop. Yeah, but no, like you need to be comfortable with programming, and maybe knowing how to use Python is also enough. So duration of this workshop is 90 minutes approximately, and then there will be half an hour for questions. Yeah, it's already answered. How to decide which application function to use from Keras. Yeah, if you're talking about these applications here, so my suggestion would be to go with small models first, like Exception or ResNet. So they are pretty like this particular ResNet 50. So they are they're reasonably accurate. So you can see how well it performs on ImageNet. And if you really need to have a strong model, you can pick something like Inception ResNet, which is a larger model, but it's more performant. But of course, since it's a larger model, it's slower. And then there is even larger model like this one, NASNet large. But my recommendation would be to go with Exception or ResNet because they are small, they are fast, they're easy to tune, they're easy to train, they're easy to experiment. And you start with them and you try to deploy them and see how it goes. And then only then you try to go with heavier models. So my recommendation would be to start with simple models. So number of layers, it's again trial and error. Yeah, you just try different things and see how well it works. So the important thing here is you need to have this validation data set, which you always use, which you constantly use to see if things you're trying make sense. So you really need to have this validation framework set for you. Yeah, what is this exception model? You can just go and check. Yeah, exactly. So, and you go to Keras applications and you check that. Yeah. Can we use PyTorch to achieve the same thing? Yes, definitely. Yeah. Thanks for answering actually all the questions. Yeah, I think these questions we can cover at the end probably. Okay, so let's. That's I don't know if it's a question for me. Have I used average pooling and not max pooling? Yes, we just did. We just used average pooling, but instead of, I typically try not to design, not to implement neural networks from scratch. I usually take existing ones from Keras applications and try to fine tune them. So I don't try to come up with my own architectures. One is because I'm not that proficient there. So there are people who are a lot smarter than me, way more smarter than me. They took a lot of effort to come up with a great architecture of a neural net. So I just want to use what they came up with. So I don't want to implement my own thing because I know it will be worse than what they did. So I typically just take what is there and then try simple things to add simple things on top of that, which is something like here. So we have our first model. And of course, I said that we need to experiment a bit with learning rate, and this is the best one. And yeah, so the next step that we have here is we want to make the model a bit more complex. So let's take this piece of code. So I'll just put it here and copy it. So what we want to do now is we want to make it a bit more complex, and we want to add more things here. So far we have only one model, only one output layer, only one layer, dense layer. We want to add another layer between vector and output. So let's call it inner layer. So, and you see like it goes like from vector goes here, so that this inner need to go to outputs. So this is the inner layer we have, and it will have a dimensionality of 100. There is no particular reason why 100. 100 is a good number, so I just go with 100 because I don't know a better number. And then when I experiment, I try to come up with a number that is 50, and then like smaller number, and then higher number, and then just see what works better. So in this case, we'll take a number 100. And when we add two layers, our model becomes more complex, and we need to add an activation function between these two things. So again, if we want to talk about activations, this is the best resource that talks about them. In my book, I also talk briefly about activation functions, but I do not go into details, and also I will not go into details right now. Instead, I suggest to check this course. They also talk about, they really discuss it in detail. So go to this website, to this course. They have all the videos available. There are class notes, so you will find all this theoretical information there about this. So we'll use the activation function. So, and currently the standard, like the best activation function is rectified linear unit, I think it's called. I don't really remember what it stands for. It's called ReLU. So we use ReLU here. And this is our model. So what we can do here, so we can, of course, right now train it once more time. So because our model became more complex, a bit more complex, to save us a bit of time, we can already add an extra layer here, or not a layer, an extra thing here, which is called dropout. And I will explain what dropout is. Let me first define it. So as we need to define a drop rate, I will tell you what it is in a second. So again, like inner goes here to drop out, and then dropout needs to go here. So what will happen when we do this, when we add dropout? So I have a picture here that shows what it actually is. So this is like a neural net. So we have two layers connected to each other. So this is the inner layer that we have with 100 neurons. This is another layer we have with I don't know, 10 neurons. So what happens with dropout is dropout randomly chooses a few nodes that it drops out, and by dropping out, it means that it freezes them. And when we train a model in one epoch, these layers are these nodes. The weights for these nodes are not updated. So which means that because it happens at random, at each iteration, a random subset of nodes, neurons, are dropped out. So this helps to generalize better. So our model doesn't overfit. And by overfitting, I mean, like, let's say we have, a t-shirt, right? And then if we feed the same t-shirt over and over again to our neural net, so it will see, okay, if there is this thing here that we have here, then, okay, this is a t-shirt. And this is not what we want the model to recognize. We want to recognize that, okay, like there is this kind of thing here, this kind of thing here, like the sleeves, and then there is the neck and things like this. Right? So we don't want the model to overfit on other things, or on the interior, on the background of the t-shirt, right? We want it to focus on the t-shirt. And the way we do it, and of course, like our neural net doesn't really look at the picture, it looks at the vector representation that we get from the base model. So it just says, I don't want to look at the entire thing at once. I just look at part of it. And from the parts, I want to try to understand what it is on the picture. So like equivalent would be like, okay, we just remove some parts of this picture and try to understand what is on this picture without looking at the entire thing. So it will be like a rough equivalent. Of course, this is not exactly how it works, but this is a good, how to say, a good idea to think about this in this way. So this is dropout, and this is displays some sort of as a regularization technique. So it's a regularization technique that allows us to fight overfitting. And yeah, so we can now train this model. So I think these are, I don't remember, I think these are the best parameters for this model. And yeah, so we can just execute this. But before we do this, so we can see that when we look at this graph, so we see that so first the model wasn't good, then it became better, then it suddenly became worse, and then it again became better. So it's a good idea to actually remember all these good things like this one and this one. So the model at this stage, and not think about the model at this stage. So what we can do for that is there is a process, there is a concept called checkpointing. So every time we see that our model improved, we save the weights. So we checkpoint the current status of the model. And this way we make sure that at the end, when we finish our training, we make sure that we, let's say if this was our iteration before the last one, and then on the last one, there was a sudden drop. So we make sure that we actually save the best model from the iteration before. So this is why we need checkpointing. And for that, we use a thing called callbacks. So every time the model finishes one epoch of training, it invokes a callback. And checkpointing is one of the callbacks. So it just checks, okay, what is the previous best weight? What is the current previous best score? What is the current score? If the current is actually better than the previous one, and then it saves the, if it's better, if it's improvement, then it saves the thing. So in Keras, we have these callbacks. There are many different callbacks, and we are interested now in model checkpoint callback. And we need to set up to say how the file name will look like. So we can say exception. So we also want to remember what kind of epoch it is. So we will see how it looks like at the end. So this is like just a template for the file. And then we say that we also want to know what is the validation accuracy. We want to look at 3 points. And then the extension of this file is H5 because this is the format we use. The metric we want to use monitor. We want to monitor validation accuracy. And by monitoring, I mean we want to see the moment when we improve the validation accuracy. If it happens, we want to save it. So this is what we mean by monitoring. So best only, again, here it means that we only want to keep the best model so far. So we don't want to check on every iteration. Of course, if we say save best only false, then we checkpoint on every iteration, but that creates a lot of files. And then sometimes, so validate for accuracy, we want to have accuracy that is as high as possible. But some things when we optimize, so for example, if we care about root mean square error or something like this for regression, then we want to minimize it. So in this case, we want to have accuracy as high as possible. That's why our mode is max. So we define this. And now we can train a model again. So let me just copy this. Yeah, so we will, let's say, usually because we now added, the model became more complex, and also we added dropout. 5 epochs is not enough, so we needed to have like at least 30. We will not have time to train a model for 30 epochs right now, so I'll just pick 5. But when you want to reproduce it by yourself, so I suggest here to put a relatively big number. You can put even 50, because you have checkpoints, and even if model becomes worse, you still keep the best checkpoint. So, but for now, we will just go with 5. And here we want to say that our callbacks is this. So this model checkpoint callback. And let's train this. So now it should, yeah, it already started training. So let's see. Okay, our GPU is utilized as well. So it will take a couple of minutes for training. And you see that for each epoch, there are 96 iterations. So there are 96 batches of 32 images in each batch. So every time we take a random subset of images of 32 images and put this into a neural net. And then, so this is when we decide at every iteration, a neural net decides which nodes to drop out. So dropout is only set at each iteration. So at each iteration, it randomly drops out, in our case, half of the nodes. So half of the nodes are dropped. And at each iteration, it's a new half of. So every time it's a randomly selected subset of the nodes. So, okay, so we can now take a look in our file system. So we see that, this is our model. So far, at each step of the model, it was actually improving. And you see this model is actually 2% better than the model we had previously. So I don't know, the fifth iteration, probably actually the fifth iteration was even more. So here we got lucky and every iteration was better than the previous one. So, and now all the weights are saved. So we covered dropout and image augmentation. So let me quickly check if there are questions. So pause video. I think maybe all the questions are already taken care of. So maybe it doesn't. Let's come back to the questions at the end of the stream. So what I will do now is so now what we do is before that I didn't mention it here. So we so far tried the model on small images. So these images that we have, they are the shape of their shape is 150 by 150. We can actually try larger images, and this other thing, yes, we also wanted to cover image augmentations. So let's start with image augmentations first. So I have a notebook here that I prepared, yes, about augmentations. So augmentation is a process of generating new data from the data you have. So let's say you have this t-shirt. So let me open it. The t-shirt here. T-shirt here. I don't know what happened here. So we have a t-shirt here. What we can do is we can flip it maybe horizontally. So this logo goes here. So that's one of the things we can do. We can slightly rotate it. We can change the color a bit, make it darker or make it lighter, things like this. And it means that from one image, we can generate many, like an infinite number of new images. So let me just quickly show you an example of what we can do. So there are many different transformations that we can do. So this is our image that we want to modify. So what we can do is we can do many different flips. So we can flip horizontally, vertically. So for us, horizontal flip doesn't make much sense because usually if you take a picture of clothes, you try to put it, you don't put it upside down usually. But vertical flip might make sense because, well, you have many different t-shirts and so this is, I think, a good augmentation to include. So every time when you decide which augmentation to include and which is not, so you should use two things. So first you should use common sense and think if it actually makes sense to include augmentation or not. So in this case, it doesn't because like you don't typically have images like that. But in some cases, like maybe you have t-shirts that are not properly placed, for example, then, for example, a small rotation is useful to generate more data. But big rotation, again, maybe it's not useful because if you take a picture, you put it more or less properly before taking a picture, so you don't just take it from random angles. So like you use common sense. And the second thing is, again, you use cross-validation, use validation. So you try different subsets of augmentations, and you see that if your accuracy improves or not. but start with common sense, because otherwise it's just too many things to try for validation. So you can, as I said, you can flip an image, you can rotate an image, you can move the image slightly. So in this case, you see like this is the original one. You can put it a bit up, you can put it a bit down. But again, if you put it up too much, maybe there is no t-shirt left, or if you put it too much down, then again, it's cut. So like you again think what is a reasonable reasonable number, like how much you want to, and this is, by the way, I think it's percent. So you want to move it by 15% down, or you want to move it 15% up. And again, you can move it to the right or to the left. So there is a special transformation called shear, which is let me try to again annotate. So this is like your original t-shirt, and then you try to make it like that. I don't know how this figure is called, but like this sort of geometrical transformation. So maybe like a small shear is useful, but you don't want to go to actually to modify the image too much. And yeah, so there are many different things you can do. You can zoom in a bit, you can zoom out, so you can make it smaller, bigger. Yeah, you can only use one dimension to zoom. So for example, you can zoom on the X dimension, you can zoom on Y dimension. Usually you would zoom on 2. And we don't need to do this manually, because we can use image generator for that. So the same generator we used here. So remember that we used this image generator here. It can already do these augmentations for us. So let me show how it looks like. So we can say, okay, we want to rotate our images from minus 10 degrees to 10 degrees. We want to shift them slightly 5%, from minus 5% to 5%. We want to zoom them a bit. We want to sometimes flip. And this is the kind of images it generates. So you just take image data generator. You see that from one image of a t-shirt, we can generate 10, and we can generate thousands and thousands of new images. And each image is different from the previous one. So this is a good, again, good regularization technique, because the neural net doesn't see the same image again and again. So it cannot overfit on a particular pixel in our image, but it will try to rather generalize instead of doing that. So it will not overfit on the position of this logo, because the logo is in different positions every time. And yeah, so what we can do, as I said, we can use the generator. So let me just copy it from here and put it to our notebook. So yeah, I'll just reuse the same thing. So, and we need training and validation. For validation, for training, we do apply all these augmentations, but for validation, you do not do this, because you want to leave your validation as is. And of course, you want to keep this pre-processing function, because this is our model expects images to be prepared in this way. So this is what we do. So maybe like it's too much. Maybe let's just remove some of them. We'll just have just a couple of different transformations. And yeah, so and now when we train, we will have a different data set every time, a different image generated from an original image. And what we can do next is we can also increase the size of the image. So previously, so usually when I start training a model, I start with small images, because we can iterate very fast. So with a small image, I try to find the best parameters, try to see like how large my neural network should be, how many layers and things like this. And when I experiment, because with a small model, I can experiment fast, and then at some point I make it a bit larger. And do a few iterations. So because this, when you take bigger images, your iterations become 4 times slower because the image becomes 4 times bigger. And yeah, as I said, for validation, you don't add any transformations. You only add transformations for training. And yeah, sorry, comma here. Yeah, so we have this. Then we need to change our base model as well. Where is our base model? So, and we need to now, probably it will try to download that model. I don't know, because now no, it uses the same weights. And we also need to change our input to have larger images. Yeah, so we have that, and we train a bigger model. So now with these settings, if we train this model for a large amount of for many iterations, I'll call it exception 2. So if we do this, yeah, so I'll just do this for 5 iterations. But here, if you let's say run it for 50 iterations, then you should have a reasonably good model. And you see this now is training a lot slower because we use bigger images. So here we will not wait till it finishes. I think you get an idea. So now this model, because it uses bigger images, it should be more accurate. And because we went through all this, like we added an extra layer, we added dropout, so this model should be better. And we also added data contation. So what we want to do now is we want to try to use this model. So to actually apply it to our images. So I think I have a notebook somewhere about this. Yeah. So I will just show you. So I will not live code it. I want to show you how to use this. But yeah, just to save a bit of time because I see that we don't have a lot of time left. So I'll just show you how to use it. So we use the same model. And so these are labels. So we know that for 0 it's dress, 9 is a t-shirt. And here in this example, we use a model that I trained previously. So it has almost 90% accuracy. And yeah, so we have this picture of pants that we load with this function load image, the same one we used previously in our in the previous notebook. So we load the model. So to load the model, we use this keras.models.load model. And yeah, so we specify where the model lives. So this is one of these files that we have here. So what is yeah. So for example, this one. So we just take this H5 file that we have from a checkpoint, and yeah, you can just load this model. So you have a model, and then you take a picture of your pants, for example. So in this case, we just take a picture from the test data set, but you can just take your phone and make a picture. And yeah, so we do some preprocessing here. So first we need to turn this image into a NumPy array. And then we need to apply this preprocessing function to this. And then we just simply invoke model.predict. So this is what we do with our model. And this is how predictions look like. So remember I said that this is a number from -infinity to infinity. Usually it's a number between, well, in this case, it's between -5 something, like -4 something, to 10. So what we're interested here in is, so we can look at these numbers as scores. So we're interested in the largest score. So in this case, we have a score of 10. This is the largest score. And the position of this is 0, 1, 2, 3, 4. So for us, this is pens. So the model is correct. And yeah, so we can just use this argmax function, which returns the position, the index of the largest score here. In this case, it's 4th. And we just use the labels that we have from here. Say, okay, this is indeed pants. So this is how we use the model with Keras for applying it to our images. But the thing is, you typically don't want to put this thing in production. So because it uses TensorFlow, it uses Keras, it's too large, it's not optimized for actually serving, it's not optimized for predictions. It is optimized for training. So with training, it's good, but if you want to use this for predictions, you need to use something else. Usually, you use a thing called TensorFlow serving. Like maybe you heard about this. Okay, I will not go there right now. So you have multiple options. So usually, like if you want to serve it, you go with TensorFlow serving. We will use a different thing called TensorFlow-lite. TensorFlow-lite is it's also a framework for serving, but this is for serving on mobile phones and different devices, like smaller devices. And we will use AWS Lambda for that. So Lambda, for those who don't know, so let me just go to Lambda. So this is a service in AWS. It's called Lambda. So what they promise is that you can run code without thinking about servers. And this is true. So you don't need to rent an instance. You don't need to create an EC2 instance. You don't need to create, I don't know, a Kubernetes cluster. You don't need to worry about that. What you do is you just define a function. You say, this is the input of my function. This is the output of my function. So you do something inside, and then you just run it. And yeah, and you only pay for the time this function is actually run. So if your model takes 1 second to make a prediction, you only pay for 1 second, right? And you don't pay for anything else. While if you rent an EC2 instance, or like if we're talking about this Jupyter notebook here, like even if I don't use it, I'm still paying. Maybe I should actually turn it off because I don't want to pay for this. Yeah, so now I'm not paying for this because we don't need it. Yes, so what we want to do is we want to take this model and deploy it with Lambda. So for that, as I said, we will use a TensorFlow-lite. Yeah, so I already have some models here, some functions here. So, well, let's take a step back. So what I want to show you now is, yeah. So what I want to show you is how you can actually turn a model in TensorFlow-lite model. So we trained a Keras model. So we saved it as a H5 file. So what we want to do now is we want to turn this H5 file into a TensorFlow-lite file. And it's actually not that difficult, like in sorry. What was it? Yeah, so the code, so let me enlarge it. Yeah, so the code for this is relatively simple. So you just, again, use this Keras models dot load model. So you load the model. And then there is a thing in TensorFlow called TF-lite converter. You just say, okay, this is my Keras model. I want to convert it to TensorFlow-lite model. And that's it. So you just execute this file and you get this file here. So you have this file here. This is a converted model. And that's it. Now we can use this model with TensorFlow-lite. So yeah, so let me show you. I already showed you how to actually use Keras model for predicting. So now we can convert this model. And yeah, so when we have TensorFlow-lite, it's a bit different. So the code is a bit more complex than simply calling model.predict. So in TensorFlow-lite, it's yeah, it's a bit more verbose than this. So I will not go into details because you can just go to the GitHub repo and check how it's implemented. But there is some logic. So first, we want to load the model, the TensorFlow-lite model, and we want to say that okay, this is the input, like this is the image we have here, like this image of pants. And this is the output. And yeah, so this is how we get the predictions. And the logic is approximately similar. So you again have an output that looks like this. So you have an array. and you just turn this array into a bunch of numbers, a bunch of like predictions here. And yeah, so for us, it's bands here. Yeah, so this is how it looks like. One thing here is like we need, remember I showed you that when we prepare this X file, this X numpy array. So here we rely on this function called, yeah, here it is, preprocess input, which takes an image and does some transformation with this image. So it turns it from like usually the image, the values there in the array are from 0 to 255, and then it converts it to a range from -1 to 1, right? And you have this function as a part of TensorFlow Keras applications, right? And you need to use this function, right? When you want to deploy your model, because when you send, like when you take a picture of something, you need to pre-process this picture so it's in the same way as the model expects. Sorry, one moment. Yeah. Yeah, so we need to use the same function as previously, but the problem with this is we don't want to take the entire TensorFlow with us. So it's not really possible to put entire TensorFlow in Lambda. And even if it is, I think now it might be possible to actually do this because we can use a Docker image in Lambda, but it's just too large to use. That's why there is a project that I'll show you now. So, yes, it's called Keras Image Helper. So what this project is doing is it simply takes this function from Keras and puts them into a separate library. So here, the advantage is you don't need to take the entire TensorFlow with you, like all these 2 GB of code with you into your Lambda function. You just take the code, this pre-processing logic with you from this library. So this is the same code as in Keras. So actually, it's a copy-paste code. So I can quickly show you how this preprocessor. So this is the preprocessing function that we use. So imagine that this is the code that we need. And for this simple code, for these 2 lines of code, we don't want to take the entire TensorFlow with us, right? So it makes sense to put this code outside and yeah, maybe to a library and then use this library. So you don't actually have to use this library. You can just simply take this 4 lines of code and put it in your Lambda function. So coming back to the Lambda function, so we will need that in the Lambda function. And we will need this TensorFlow-lite you will need to use TensorFlow-lite for loading the model. Yeah, so that's what we need to do. And I will just quickly show you the code for doing this. Sorry for going a bit slow. I think if I do live coding here, it will take another hour. And I'm a bit tired of live coding by now, sorry. So I will just quickly show you how you can do it with Lambda. So so in Lambda, so here, let's start from the end. So this is the actual function, this Lambda handler. This is the actual function that we invoke within Lambda. So this is the input we get. So when we have a picture and we want to predict what is the class for this picture, what is the type of image we have on this picture. So the image actually goes here to event. Then it's a URL. So we take this URL, then we load the image from this URL. Then we apply our model to the image, and then we do some post-processing. So here, like when we get a model from a URL, when we get an image from a URL, we turn it into, like, we basically load the image using the same logic as we did with Keras, and then resize it, and then do this post-processing. So we here say that we want to have, so this is an exception model with this target size. So it's 299 by 299. Then we say, okay, this is our model that we want to use, and yeah, some boilerplate code for loading the model. And then actually, this is our predict function that invokes the model. And at the end, we just get back the raw predictions, which is NumPy array of with 10 numbers. And then we turn these 10 numbers into an actual class using this decode function. So this is what our Lambda function is doing. It's relatively simple, like it's only 50 lines of code. And all this code, as I said, is available on the GitHub repo. You can go and check and try to understand what is going on there. And yeah, so this is the entire file. And what we want to do now is we want to take this file and we want to deploy it with Lambda. Yes, for that, we will use Docker. So Lambdas support Docker. So if we go to Lambda, so we can say, okay, we want to use a container image for serving this model. So we want to use a container image for serving this model. And then, yeah, so there are some parameters. So let's quickly try to, okay, so there is a Docker file. So in this Docker file, for those who don't know, Docker, it's just a way to put all the dependencies, everything you need for running the code into one single image that contains everything. So this image is self-sufficient, so it has everything you need. So here we install all the libraries we need. So we install Keras image helper, the library I showed you, and we install TensorFlow-lite. Yes, we install it here, TensorFlow-lite. Then we take our model and copy it to the Docker image. And then we copy the Lambda function, the function that is doing this, like this 50 lines of code. So this is what the Docker image is doing. Then this is an official Docker image from Amazon. And yeah, so what we need to do now is we need to run this to build this Docker image and deploy to AWS. So maybe I can quickly show you how to do this. I think what will be even more interesting, so to actually run it locally. So this is, so what I'm going to do now is I'll take this image and we'll try to build it. Okay. So I need to apologies. Yeah, I think I need to enlarge my font a bit. Okay, this should be better. So what I will do now is, let me just clear everything I have here. So what I will do now is I want to build the image, this Docker image that I showed. So I want to build it. Okay, because I did this already, it was fast. So for you, when you run it for the first time, it will take a bit of time. So what we want to do next, so we have an image locally. So now we want to run it. So let me open this README file. And by the way, this README file is also in the repo, so you can just follow along with instructions if you want to run it. So now we want to, so we build it locally. We want to run it locally as well before actually putting this to Lambda. So we execute this command. So now it should say, okay, yeah, it's ready, I think. Yeah, well, so we have that. So now our model is running, so we want to test it. So we have a special file, that test.py, test.py. So what it has an image. So let's open this image. I think it's an image of pants. Yes, this is an image of pants. So we have, so this is our request. So we have a request which has a key URL and then the URL of the image. And then this is our thing deployed locally. So it's deployed on localhost inside Docker. And what we do is we simply send a post request to this using this with this request, and we will get back some result. So let's run this code. Okay, it takes a bit of time because yeah, I don't have a GPU on my computer, but yeah, now it gives some predictions, and we see that here we have pens, and for pens the score is highest. So this image is an image of pens. So this thing is now running locally on my computer. So because we have it here we just run it here. It's smaller. So it just runs in a Docker container locally. So what we want to do now is we want to get the same container and deploy it on AWS. So for that, where is the README file? Yeah, so what we need to do is, I think I already put it in my Docker registry. So there is a service called ECR on AWS, which where this is a place where you put Docker images. I think if I try to run it now, it will say, okay, it's already there. Yeah, it already exists because I already created it. And now, so what we want to do is we want to take the image we just built locally and we want to publish it there, to put it there. So first we need to log in with ACR using this command. Sorry, I know I'm moving fast, but this is all available in the README. So you can later maybe just open this file and move along with me. And yeah, so you first log into ECR using this command. And now you can publish your image. So in this case, the image is so your region, account, so it should follow this template, and you can just publish it. So now it's publishing to this particular repository. So now we have this in ECR. And ECR is, as I said, the Docker repository in AWS. Go there. ECR. Yeah, we have Elastic Container Registry, which has all the models. Yeah, so and we have this image Lambda images. So yeah, now it's pushing, but we can just use the previous image that I have here. So the TF-lambda, which was pushed there quite a while ago in January. And then there is image URI. This is something we will need right now, so we can just copy it. And now we go to our Lambda function. And we can say, we now will use this image to actually create Lambda functions. We can just call it clothes model. And then now we need to put the container image URI. So we just copied it. So I just copied it. So I put it here. And yeah, I don't think we need to change anything else here. So let's just create a function. Okay, we have a function here. So what we need to do next is the default configuration we have for our model is not sufficient for us because it doesn't give us enough memory, and the default timeout is simply it's simply not enough. So we go to, I think they changed this slightly. Maybe it's general configuration. Yes. So now, so you go to configuration, then you go to general configuration, and then you click edit here, and you put instead of 100 megabytes, you put 1 gigabyte, 1024 megabytes, because we use a big model, so we need some RAM for that, and we give a higher timeout, because for the first time when we run our Lambda function for the first time, it takes some time to run it, to load everything in memory. So that's why we give it a bit more time to actually do this. That's all we need to change. So just give it more memory, give it more time to execute, and now we can actually test it. So we have our model. We use the image we just created. So what we can do next is we can so probably here test. Okay, yeah. So now we can test it. Yeah, sorry, I think they changed the interface recently. I'm not yet familiar with the new interface. So where's this test? So we want to send the same request as we did locally. So this is the image of pens. Yeah, so this is our request. So we have the URL and then the URL of pens. And yeah, I don't know if we need to, let's just save it. Test, save changes. And now what we will do is we will just click test. And what happens now is Lambda functions goes to ECR, to this Docker repository, pulls the image from there to the Lambda function. Then it also starts it, loads everything into memory. Yeah, it takes a while for the first execution. That's why we need to give it a bit more time to actually run it. So it took some time, so we can actually check how much time it took. So it says that it took 13 seconds. Most of this time was actually used for fetching the image, Docker image from ECR. Because when we now execute it second time, so let me just do this, it should be a lot faster. You see, it just took 2 seconds. So because everything is there, the Lambda function is so-called warmed, because it's already awake, it's already ready to serve requests. So that's why it's a lot faster. And all the consequent queries we do to this service, like now you see it's again faster. So it takes 2 seconds. And yeah, if you go to like if you want to know how much it costs, it's really fractions of cents, but you can go to Lambda price calculator. I think there is a good website, yeah, Lambda pricing, and you can yeah, now that there is like a widget, dynamic widget you can use to see how much it costs. So I used region in Ireland. So for me, it's in Ireland, and I use 124 megabytes, and this is the price I pay for 1 millisecond. So actually for 2 seconds, so I need to multiply it by 2000. This is the price I pay. But again, like to make it more concrete, let's say if we want to make a prediction for 1000 images, we pay 3 cents, which is not too expensive. And the good thing about this is that here you don't pay for the time when you don't score images. So you only pay when this thing is actually running. So this is the beauty of it. Of course, when you start getting a lot of images, let's say when you have 1 million images, then it becomes more expensive. And if every day you need to score 10 million images, then every day you need to pay $300. which becomes more expensive. So then if you need to deal with that high volume, then you probably need to use something like Kubernetes. But this is out of scope for today. So what I also wanted to show you, I do not have time to do this now, is so I showed you how to invoke this from the Lambda, but maybe this will be a home assignment for you. Is now you can expose this as an API using what's called API gateway, I think. Gateway. Yeah, so there is a thing called API gateway, which allows you to actually execute this thing Lambda as an HTTP service, as a HTTP request. So I will not go into details right now, but you can just know that you can do this. So I think, yeah, so you can create a REST API here. And if you want to know how to do this, again, you can, I can share a link with you. This AWS Lambda Docker, which explains everything how you can do this. So there is like everything I explained here, plus creating Lambda function. And here, like this is the last section, is how you can create the API gateway for doing this. So I will just quickly post it here. You can refer to this later. Yeah, I think that's all for the main part, and I can take questions now. I don't know, should I read the questions myself, or? So. Okay, I guess I can just go through the questions. Just in case, I'll refresh it to make sure that I get the. So let's start with this question: AWS or Azure? I do not. I have never used Azure, so yeah, I only used AWS. I also used a bit of Google Cloud, but at Elix I use AWS. At two previous companies where I worked, I also used AWS. So I don't really have experience with other cloud providers. But for me, AWS has everything that you need for deploying deep learning models. And so you can use Lambda functions from there. You can also, if you need to deploy something larger, you can run the Kubernetes cluster there. Yeah, so there are many things you can do with AWS. And of course, like let's say, if you go with Azure or if you go with Google Cloud, they all have basically the same functionality. So in Azure, you have Lambda functions in, like something analogous to Lambda functions you have in Azure. Then you have something analogous to Lambda functions in Google Cloud. So I think all these things, they translate really nice from one another. So you just call things with different names, but at the end, like each of them has a file storage. If each of them has some sort of serverless functions, each of them has a managed Kubernetes cluster. So at the end, like the concepts behind each thing is similar. So indeed, the link for API gateway is gone. I don't know why, because maybe YouTube thinks it's spam. So what I'll do now is I'll send it to Zoom chat, and I'll ask to actually the Hemant to put it in YouTube. I think that should work. Yeah, sorry about that. Yeah, but the way you can find it is you can go to my account. Sorry. So this is my account, Alexey Grigorev. And there is a repo called AWS Lambda Docker, which you can also, if you have a copy of my book, then you also have all this information there. But it's also available for just as a GitHub page that you can refer and just follow. Okay. So I'll move to a different room now, sorry. Okay. I don't know if this is the best way to ask me questions. Should I maybe scroll up if there are any questions? Can I use this method for live image tracking in NVIDIA Jetson? I think you can, yes. So with TensorFlow-lite, you can actually deploy it in Jetson, and you can do everything I described here with Jetson. Of course, here the example I showed is it's not the same as live tracking. It's a little bit simpler, but yeah, I think you can find a lot of tutorials online how I can do this, also using TensorFlow-lite. Yeah, if you want to ask something, you can just ask now, because to be honest, like to me, it's difficult to know which questions were answered, which not. So you can just ask me something here. Yeah, if you can help me to send some questions to Slack, for example, please do. Because I don't know which questions I should answer now on, or which you already tackled. Okay, so I get a suggestion to go to the top, and I will do that. I don't think I have all the questions here. So I think I answered that about PyTorch. Yes, which is the best one, Keras or PyTorch? I don't think there is like, it's just a matter of preferences. If you like Keras, you can use Keras. If you like PyTorch, you can use PyTorch. At the end, it's you can do the same thing with both. It's just a matter of preferences, in my opinion. I don't think you can say that one is better than another. So there is when it comes to TensorFlow and Keras, the reason I like them more than PyTorch. I haven't used PyTorch a lot, to be honest. So that's another reason why I mostly use Keras, because I don't have much experience with PyTorch. But there is one thing that I really liked about TensorFlow is TensorFlow serving, and another thing is TensorFlow-lite. So these two libraries make it a lot easier to actually host models. So they're time proven, they are good, and it's more or less there's a community that knows how to serve these models. So when it comes to production, I think TensorFlow is still a bit ahead. I might have outdated information, because I know that PyTorch is really catching up with TensorFlow. So maybe somebody who is listening right now will say, no, this is not true. And it might be the case as well, yes, because I know that PyTorch is gaining popularity, and it's just a matter of time when there's PyTorch serving is as good as reliable as TensorFlow serving. So there is PyTorch serving, but it's a lot younger, I would say. So maybe it's still more fresh than TensorFlow serving. Yeah, but it doesn't matter, you cannot use it. And then also there's a thing called Kubeflow serving. And with Kubeflow, it doesn't matter which model you have. So with Kubeflow, you can serve TensorFlow model and you can serve PyTorch model. And then you don't care what is actually inside. So you just say, hey, Kubeflow, so I have a TensorFlow model. It lives in this location. Just load it and start serving it. Or I have a PyTorch model, load it and start serving it. And this is really great. So if you want, I do recommend checking Kubeflow. It's a nice tool, and I think in a couple of years it will become more quite popular. Yeah, can you please plan a beginner course on TensorFlow? Yeah, so this I guess is not a question to me, but actually what I presented, I know I was fast when talking about some things, but if you take your time and walk through this tutorial that I presented today, walk through this part at least at the beginning. So I know I was super quick with Lambda, that's for sure. But the part when I was training the model, if you, after this stream, if you, at some point when you have some time, if you try to follow this along, and you also try to read the thing I suggested about this course, I think it will become clearer. And I really like, I really believe in learning by doing. So if instead of, just, watching a course, you try to do something yourself, just try to follow this, you will understand how it works a lot better than, so I think this is, so what I'm trying to say, I think this is actually good for beginners. So if you just start, if you already know how to use Python, if you know how to use NumPy, if you know how to do simple plots, then you can just take some time, walk through this tutorial in your own pace, and this will already give you a good understanding of what you can do with Keras and TensorFlow. So how to decide epoch? So I think this is like how to decide the number of epochs, right? And yeah, so simply like there is no, I don't know if there is a good answer. So what I usually do is I just pick a big number, like 100, for example. And then I try to watch, so here you see that when you train a model, you see these kind of things, this kind of output. And you can see that, okay, at some point your model stops improving, right? So maybe, so here it's 87%, that it becomes 89, then 89, and then it doesn't go above 90. And then maybe it goes down or things like this, then you know that you need to stop. And what you do next is you just click the stop button. You just interrupt the kernel. This is how I do this. So to say it again, so I just pick a high number, I watch these logs, and when I see that it doesn't improve or it becomes worse, I stop. And then this is how I know for how many epochs I need to train. Yeah, it's, I don't know if it's ideal, but like if you're in this, when you are in this exploratory mode, when you're just trying different things, I think this is the best thing you can do. What do you want to suggest for a beginner who is learning machine learning? Well, of course, I can suggest my book, but maybe this is a bit biased suggestion. But if you're a developer, if you have some experience with coding, yeah, this is, I definitely recommend checking it out. And you don't have to buy it. You can actually go to the Mining's website, and there is you can read it from the website for free. So, and decide if you like it or not. One thing I personally used when I started learning machine learning was a course from Coursera by Andrew Ng. It's a relatively old course, like I think it's 9 years old right now, but this is a really great course. So I think it makes sense to go through this at least once and try to implement all the exercises in Python. So I do recommend checking that out. Yeah, and then on the internet, like I think there are so many courses right now. It doesn't really matter which course you take. You can just pick a course and finish it instead of trying to find the ideal course. It doesn't really matter. There is no ideal course. You just pick one and you try to finish it. And after one course, maybe you're still clueless, right? So this is what happened to me. I watched the course by Andrew Ng. I really got excited, but yeah, to me it wasn't still. Yeah, I couldn't still say that I got this. And then I watched another course, and then I watched another course, and then it became clearer. And later I heard about a thing like a concept called the rule of three. And the idea behind this concept is that you need to study, I think, when you're studying, I think, in order to understand it, you need to read about this or to watch it, or I don't know. You need to consume from 3 different sources. It could be 3 books, it can be 3 courses, it can be 1 book, 1 tutorial, 1 course. I don't know, but it should be 3 inputs. And when you do this, then you get it. And at the end, maybe it doesn't really matter which course it is, like as long as you try to consume it from 3 different sources. So instead of, let's say, reading the same book again and again 3 times, it's better to read 3 different books, and then you will get it. Because different sources, they teach you things from different perspectives. So if you take my book, for example, it's really hands-on. So I don't talk a lot about theory. But if you take some other book, maybe they focused on theory. And if you take a course by Andrew Ng, this is a great course. It teaches you basics really well. And with this, you will already see the same thing from 3 multiple angles. And this is great. So my recommendation would be pick 3 things, doesn't matter which ones, and learn from them. Keras application models are more comprehensive than the PyTorch ones. Maybe, I don't know. How to choose a pre-trained model. I think I covered that a bit, so I will not repeat. So I'll go about this, the activation function in the last dense layer. So even though I killed the notebook, it's still, the code is still there. So let me go back to this. So indeed, if you, like, maybe let's take this example. So in this example, for the inner layer, I did add activation, right? So I added relu. So we have here, but for the output, there is no activation, right? You can, of course, add activation. So you can say activation softmax. So this is what you like, because our problem is multi-class classification problem. So we have different 10 different classes, and we want to predict one of them. Typically, what you want to choose at the end is a softmax activation. So because it normalizes all the scores you have to, so it looks like a probability distribution. And when you sum all the 10 different outputs, they all sum to 1. So this is what softmax is doing. Again, I suggest to go to this excellent course and read more about this. It's really great. Yeah, so typically you would use softmax, but here I didn't use. And instead, so let's say I use this from logits true. So this is what you do, because the output of this thing is not a probability. It's this raw score between -10 and 10, right? So this is, you can call it logit or legit. I don't know how to pronounce it. And yeah, so this is like a raw score before transformation, before activation. And yeah, so you have 2 choices. So you can decide to not include activation here, and then you use from logits true, or you include activation and you say from logits false. Conceptually, I don't think it matters. So they are equivalent. So yeah, like this is the same thing basically. It just here at the end, you will have a normalized score, and in the other case, you will not. But there is one gotcha, I think. I read somewhere that when you do this from logits true and you don't include activation, it's numerically more stable. I do not have a link with more details about this, but I think if you Google, if you go to, I think I read it in the TensorFlow documentation. So let's see if I just put this to Google, and yeah, so here this is official documentation, and I think the recommendation here is yeah, I think I read somewhere, I think it was in this documentation that yeah, it's a good idea to actually use it. I cannot find it right now, but yeah, you have to believe me on that. But like, as I said, it doesn't matter. You can do it this way or you can do it that way. at the end, the result will be the same. So outputs already has input number. Why are you using it again in the funnel model, both input and output? I don't know. I don't have an answer for that because this is just how you do this in Keras, I guess. Yeah, so like I followed the tutorials that are there for Keras, and this is how they do this. So yeah, I did it this way as well. Why not max pooling? I don't know. Like I think you can try both and just see what works better. For this particular case, I don't think it actually will matter that much. I think both are fine. What is the best way to apply transfer learning for pre-trained models? I just showed you the best way to apply transfer learning. So you take a model that is pre-trained and you try to apply it to your images, to your domain, and yeah. So this is how you do. I just showed you. So I think this is the best way. Keras or PyTorch, which is the best for developing neural nets for chatbot? I don't think it matters again. So like just pick the two you like more and use it. And then at the end, the result will be the same. Yeah, and yeah, thanks for answering that. So let me check. Maybe I have some questions here. Can this model be efficient for audio classification? This particular model, no, it will not be efficient for audio because it's for images. But I actually don't know if there are pre-trained models for audio. I have never worked with them. I imagine there are, and you can just try to find them. Maybe we can just do this quickly. Keras pre-trained audio models. Yeah, there is something. So yeah, just use Google or your favorite search engine to find this, and then apparently there is already an article with code that you can just copy paste and play with this, and then tune it to your need. I'm reading questions from the phone. Okay. Now, should we perform all the augmentation steps for test data and validation data? No, I don't think we should. So as I said, like we don't touch test data at all. So we just imagine that like let's say we only can touch test data every once in a while. So let's say we spent a lot of time tuning the model, and then this is the time when we touch the test data set to make sure that we didn't accidentally overfit. And yeah, we don't want to change it because like when let's say we want to deploy this model, when we want to put it in a phone and we want to actually use it, we don't want to do this to start rotating this image and whatnot, because it's I don't know, it's just common sense. I don't think it makes really sense to do this. Sometimes, on the other hand, people do this. Let's say you can take a picture of your t-shirt and then you can generate 10 different augmentations. Then you can apply a model to all the augmentations. And then at the end, you can take an average prediction. So it kind of means like you, how to say, you become more certain that like your model become better this way. But there is a flip side. So your model become more, like your model becomes better, but your model becomes a lot slower. Your model becomes 10 times slower. So you don't usually do this in production. That's why it doesn't make sense to use this augmentations for test unless you're on Kaggle. Like on Kaggle, it makes sense, and I think it's called test time augmentation, but this is not something you would typically do. And as I understood, that's all the questions. And I think, yeah, I think we are actually, like, it's been 2 hours since we started. So I would like to thank everyone who stayed with me for 2 hours, and I see that 73 people are still watching, well, 71 now. So thanks a lot for joining me today, for listening in. I hope you really learned something new today. Like all the links you can find, maybe I can just quickly show you once again that all the links are here. So check the DataTalks.Club. This is a great community. If you have any questions about data, if you want to help somebody, if you need help with something, you can go and join our Slack. And then if you liked the presentation today and you want to learn more, you can check my book. So there is a special discount if you want for 30%. And what is more important, if you click on this link, there is a link to the GitHub repo. And this GitHub repo contains all the code from the book. So you don't need to have the book to actually learn from this. All the code is here. And today we talked about chapter 7, neural nets, and chapter 8, serverless. So in chapter 7, we talked about training a model. So we can go here and yeah, so you can check like this. Training is about training the model. Testing is how to apply the model to the data set to get predictions. And augmentation is like I was showing you different, like how we, yeah. So these pictures, like how augmentations actually look like. So this is the chapter about neural nets. And then the chapter about serverless is, yeah, so this is the thing about deploying. So first we get the TensorFlow, the Keras model converted to TensorFlow-lite, and we deploy it to Lambda, and then we test it with Lambda. And I just realized that there is no link to the other repo I did, to the guideline. When I finish this call today, when I finish with stream, I will add a link here. So you don't need to try to find it here. You just go to the books website, you click here, you go to the serverless chapter, and it will be in README. So you will not need to try to find it. And that's all for today from me. So thanks again for joining me today. And that's all. And bye, everyone. Have a great night.